Welcome in to another new NACE International podcast. My name is Ben Dubose, and I'm a staff writer with Materials Performance Magazine. Today, as we continue our MP interview series speaking to various industry leaders, we're joined by Chris Taylor, Principal Engineer of Materials Technology and Development within the oil and gas services business at DNVGL. Chris, good morning. How are you?
I'm doing fine, Ben. How are you doing?
Doing well. Thanks for joining us. And we're also joined on this call by Jeffrey Johnston, founder and principal engineer at Rapid Prototypes. Jeffrey, good morning to you. Thanks for joining us as well.
Thanks for having me.
Sure thing. And for those listening, the reason we're talking to Christopher and Jeffrey is that Rapid Prototypes recently won the American-made Geothermal Manufacturing Prize from the U.S. Department of Energy. The Geothermal Prize provides additional funding as an incentive to further product development, with additional phases still to come as far as the research goes. The team to receive this award is led by Rapid Prototypes and comprised of officials from Geotech's Design Solutions and DNVGL, among others. The reason we're talking about it on this podcast, of course, is that there's a clear link to corrosion from their work. Reading from the press release, their strategy on this research project is to demonstrate a future suite of logging tools that can be deployed in ultra-high temperature geothermal wells. The core technology is the design and process of additive manufacturing to optimize the geometric design and unique material layering to reduce thermal conductivity between electronics and the reservoir temperature. The goal is to expand the tool's temperature rating to 400 degrees Celsius for a duration of 10 hours. So I think a good place to start, and Chris, Jeffrey, either of you can take this. As far as the origins of your research, when and why did you all start down this path?
This is Jeff here. Chris and we met in early 2019 at a additive manufacturing roundtable in Oak Ridge National Labs. This was hosted by the Department of Energy, and it was really to get industry involved in the early stages of additive manufacturing for downhole applications. So there were oil and gas companies invited, certification companies, geothermal companies. We were all involved. And Chris and I met, and we've wanted to work together on an additive manufacturing project ever since, and this provided a great opportunity to do that.
So what are some of the potential industry application areas? We talked in reading the press release about the ultra-high temperature geothermal wells. How does this eventually get used? What's the practicality of this for the industry, assuming this continues to pan out as you hope?
This is Jeff again. So right now our focus is in the geothermal market, and to develop a better understanding of geothermal reservoirs, we actually need to go into those reservoirs and make measurements. This will help us validate these models. And currently, the geothermal industry, they use oil and gas tools, known as logging tools, to go into these reservoirs and measure things such as temperatures, pressures, flow rates, profiles, etc. And the challenge is when you're using these oil and gas logging tools, they're very expensive, and they've really only been developed for temperatures that are encountered in the oil and gas industry. And these are generally lower than what's found in traditional geothermal and especially enhanced geothermal applications.
Let's talk about corrosion specifically. You touched on things that obviously can be related to it, but for our audience at NACE, that's certainly what they want to drill down more into. What does this research mean for corrosion in particular within a geothermal environment?
Yeah, this is Chris Taylor here. So there's two primary threats we're designing this tool to address. In terms of materials performance and what's going to be happening in these extreme conditions. So Jeffrey had mentioned enhanced geothermal, and traditional geothermal is using existing reservoirs where there's already hot water present, and you can create these flow cycles to drive power from the geothermal reservoir. But enhanced geothermal is looking at drilling through areas where maybe you don't have natural hot spring reservoir type systems. In that case, you're having to drill deeper. You may be in more aggressive chemical environments that you'd rather avoid, which could involve brines and sour gas, as well as higher temperatures, say targeting something like 400 C. And so you're starting to encounter a range of different threats. One of those is thermal degradation. These are logging tools, so they have electronics included in them. So the electronic components and the flash memory are all going to be subject to thermal degradation. So we're targeting that threat and trying to address the first threat of the threat to the electronics package by using phase change materials and a design for the actual tool geometry, which has minimal thermal conduction pathways in terms of the materials that we're using and the topology that we can print using additive manufacturing. So that's where we're getting an innovation piece from the AM in this design. The second threat is regarding the casing of the tool. It's going to be cased in some kind of corrosion-resistant alloy, which is going to be under threat due to the fact that, first of all, it's going to be under the mechanical pressures and tensions that's going to be placed on the device. So we want to use a high-strength material. But as you start to go to 400 degrees C, the strength rating of materials significantly drops. So we need to balance the demands of having a strong, robust casing for this tool, which can withstand the pressures and tensions being placed on the tool, alongside the corrosion resistance in the brine environment. So we're looking at a range of corrosion-resistant alloys, as well as potential claddings to place on top of that alloy, which will give it the corrosion resistance we need. And our company in DNVGL in Dublin, Ohio, has a testing facility where we can do the validation of the materials selected for this particular tool.
With over 37,000 readers, Materials Performance is the world's largest circulation magazine dedicated exclusively to corrosion prevention and control. Published monthly by NACE International, Materials Performance covers the latest technologies, techniques, and methods of corrosion control used in industries and infrastructure worldwide. Sign up for your subscription today at materialsperformance.com/subscribe.
Circling back to one of Jeff's responses earlier, he mentioned how expensive many of the current tools for this purpose are. Where do the cost savings come with regards to the system that you all are putting together? How does this provide advantages financially compared to what's out there now?
So right now, when I say that, oil and gas logging tools are inherently expensive, it comes from two things. One, it's the electronics. So when you design electronics that are rated for 125 or 150 degrees Celsius, and then you move up to 177 or 200 degrees Celsius, the costs go up exponentially with temperature. And so by allowing us to stop this exponential growth in costs, we're able to use passive techniques, like Chris was talking about, using phase change materials, limiting the path of thermal conductivity between the well and the electronics. We're able to get away from going higher and higher in electronics survivability. And so we can limit it to 200 degrees Celsius, and then we can use these passive modes to prevent the electronics from being degraded.
Let's talk a little bit more about the Geothermal Prize and the award program overall, as far as the additional funding that you get for your research. I guess if one of you could go into, number one, a little bit of the background of the program for anyone that is not aware of it, and then secondly, what's the significance of that prize to your work as you go through the future phases?
Yeah, this is Chris Taylor. The Geothermal Prize is part of, first of all, it's funded in this case by the Department of Energy. And the Department of Energy is always kind of wanting to be forward-looking and see what are technologies that the country can invest in to stay competitive and to move towards a more sustainable future. And so enhanced geothermal is part of that portfolio. But rather than doing a traditional grant or model for funding this research, they really want to use a contest to spur more innovation, more competition between participants, and one of the goals, actually, in this particular case, is it's targeting the use of additive manufacturing and computer simulation to accelerate the time to market for developing a device. Right? People have been talking about additive manufacturing and how it's going to enable all these industry transformations, and this is one way for the Department of Energy to say, okay, let's set a timeline. We'll put some markers in there to motivate, researchers and industry to work together to show that we can really do this. And it's kind of a stretch goal looking at this particular challenge of enhanced geothermal systems and how technology can really enable that, bring down the costs, get a faster product to market by fostering this kind of innovation.
So what are the next research steps? From the press release, I mentioned, I believe, 3 more phases. In terms of where you are now to where you eventually want to go, what are the next steps moving forward for this collaboration?
This is Jeff here. So currently we're in phase 2 of the challenge. In phase 1, we were really just developing a concept and proposing an idea to the Department of Energy. Mm-hmm. And in phase 2, we build on that idea. We use modeling, and in our case, we're going to be using COMSOL. They're an industry leader in multi-physics simulation, and we're going to be using that to validate our hypotheses and refine our prototype design. And so, like Chris had said, this has a real target towards additive manufacturing, which allows us to be a lot more creative in how we design the mechanical tool. And so if we're not constrained by traditional manufacturing techniques, we can come up with more creative designs that you otherwise wouldn't be able to pursue. And so in the next, or in the current phase, we're going to continue to refine and develop the concept. And then in the next phase, that would be when we actually go ahead, finish the engineering drawings, the tolerances, and we actually manufacture the first prototype. Mm. And then after the prototype is manufactured, all of the contestants will be meeting at one of the national labs. And this obviously depends on how things progress with COVID-19. Sure. But the idea is we would all get together, we would be able to show our concepts, and then there would be a panel of experts from the national labs, from the Department of Energy, and industry experts. And they would look at all of these designs and they would select a few for progress to the final stage, which is where we take these prototypes and we actually start to test them in real world environments. So we would take them up to, in our case, 400 degrees Celsius. They would put them in these high H2S environments, and they would stress the tools to make sure that they're going to operate the way we have specified we would like them to in our proposals.
So what's the timetable roughly? I know you mentioned the COVID-19 factor potentially being prohibitive in one of these phases, but it sounds like we're talking within the next few months or within the next year or two, if we're talking about COVID potentially being a factor. What sort of, when you talk about these next research steps, are you thinking when it comes to the timeline?
Well, the timeline is, I wouldn't say it's set in stone, but right now we submitted the phase 1 documentation in early November of this year. And phase 2 is going to be submitted in mid-February. And so with the documentation for this phase submitted in mid-February, we're expecting to hear who has been selected to move on to the next phase sometime in May. Okay. And then based on that selection, the 4th phase would be in probably November of next year. And then we'd be looking Q1, Q2 of 2022 for the final phase where we go through and do this testing. So for developing a new technology using a completely new manufacturing approach, this is a highly accelerated timeline. Sure.
For any of our listeners that want more information from you all, or perhaps to learn more about this project and the research that's going to be really in progress for the next few months, it sounds like, what's the best way that people can either get in touch with you all or learn more about what's going on?
For Rapid Prototypes, you can go to our website, rapidprototipesllc.com, and you can contact us through our contact page. Otherwise, you can reach out to me directly, Jeffrey Johnston on LinkedIn, or my email is jjohnston@rapidprototipesllc.com.
Yeah, and you can also reach out to me through, as Jeff mentioned, LinkedIn, Christopher Taylor on LinkedIn, or christopher.taylor@dnvgl.com.
Sounds great. And folks, that's where we will wrap up today's podcast. For Jeff Johnston and Chris Taylor, I'm Ben Dubose. And if you want more insight before our next episode, I strongly encourage you to check out NACE.org and materialsperformance.com. Also, if you have not already, please subscribe to the podcast and leave us a 5-star review. As always, thanks for listening, and please come back soon for another new podcast episode.